This section is called Transition Metal Complexes. Remember back in chapter 17, we had complexes that had a KF. And you kind of wondered, like, where did they come from? Well, this chapter is going to describe where they came from. I drew it as an octahedral right here. And what I want to do is point out some things. The chromium in the center is called the central metal, and in this case it is an ion. Sometimes it could be an actual metal. Each of these bonds, they are called covalent bonds. Notice I put covalent in parentheses. It'll be developed as we proceed to the chapter what type of bond it actually is. So the transition metal, the chromium in this case, here it is Cr3+. Notice we've also given it the name Lewis acid. The ligand. What is the ligand? Well, we have Cl- and we have H2O. Those are the ligands. And what does it say a ligand is? It's a molecule or an ion that surrounds the metal. And notice it's also given the name Lewis base. So that terminology that we had back in the acid chapter, you can see how it's going to apply as we go further. And usually a Lewis base will have definitively an unshared pair of electrons. You can see it by the charge. Or if it's water or ammonia, carbon monoxide, pH3 or NO, it can donate either through a lone electron pair or through a double or a triple bond. Again, this is really to teach you what a complex is. Moving a little further, in the beginning, people named everything after themselves. It wasn't until Werner came along in the 1890s that he did some really good chemistry to figure out what was going on. In my first slide, I didn't have an anion, but notice when I look at these modern formulations, they all have a number of anions, 3Cl, 2Cl, 1Cl, or 1Cl. And notice how there are things inside what is called the coordination sphere. So what Werner did, because when he had these different compounds, he saw that they were various different colors, and it didn't make any sense based on the original formulation. So he did the chemistry that you've seen before. He added some silver nitrate. And when he added it to those complexes that had a chlorine ion, what happened was he precipitated out silver chloride. That's some chemistry we talked about back in chapter 17. So it says he reacted each compound with some silver nitrate, and he unequivocally proved which atoms were bound to the metal. It depended upon how much silver chloride he obtained. He did grams, he did moles. And essentially, he was able to come up with the modern formulation to look at the different compounds. He's also someone who proposed valence. Now, I never stress this, but again, I don't know what's on your final. But if you use the word primary, what you're really talking about is the charge. If you use the word secondary, what you're talking about is the coordination number. And we'll get into that in a little bit, but I just want to go through this. Now, I didn't label it on the first slide, but the coordination sphere, that is the central transition metal that's bounded to a group of surrounding molecules or ions. So we have our central metal atom with our ligands, or we can say our Lewis acid with our Lewis bases. And you've seen the second one before. That's the complex involved in the KSP-KF calculation, which then people could use. So once Werner did this, he saw that there were actually two forms of the cobalt amine chloride. And there is a special way to name them, but I am just going to write them here so you can see a little bit better what we mean by what's going on. Okay, here are my amine groups, and there is my chloride group. Notice these two are next to each other. And because they're next to each other, they are called cis. If I draw this and I put the chlorines across from each other, those are going to be called trans. And again, that's terminology that you're going to use next year when you take organic. So I really need to put this around the outside to make sure people know that these are ions. And if they are across we use the term trans. So you can see on this slide how they're very, very, very different colors, and note how they look in these pictures, just in case something like that appears on your final. These are called isomers, and there's more about that later, but cis and trans are termed isomers. Here's this metal ligand bond. I called it covalent when I started the first slide, but essentially we give it a special term, and there it is where you see the electrons in between the N and the Ag. Again, it's the Lewis acid, here it's silver. It's the Lewis base, here it's the ligand ammonia, and essentially what it forms is that silver amine complex, which you had back in chapter 17. So the reason to talk about it is when I make that bond, it's going to change the properties. You guys know what an E0 potential is now. So here is our E0 reduction. Silver alone has a positive. If I make the complex, it becomes a negative. Again, just focusing on the properties. It can also have an impact on the color. I have a clear, oh, it's sitting over here in this container, NCS minus, thiocyanate, but when I have my iron, this would be my iron 3 plus, remember they're not naked, they're surrounded by water molecules. When I mix the two of them together, I get the complex, and it has a different color than either the ligand, NCS minus, or the Fe3 plus. So this leaves us to the second last slide, and it's about charges, coordination numbers, and geometry. I'm going to sketch this material, and it is in an octahedral arrangement. We're going to be talking about that in a moment. But here I've drawn my coordination complex. And there we have all our NH3s around it, and we must make a 2 plus. So it says the central metal atom or ion is cobalt. How did I come up with a CO3 plus? Well, I'm going to go over here on the bottom. I'm going to redraw the complex, and just like we did earlier in this class, I know +2. So chlorines are also a -1 as an ion. Ammonias are a -1. So I have a 0 and a -1. That forces my cobalt to be a +3. That is how easy it is. What are my ligand donor atoms? Well, in this case, it would be the nitrogen from ammonia. It has that lone pair. Or it would be the chloride ion, which also has a lone pair of electrons. Where do I get the coordination number from? It is the number of bonds, and you'll see that more apparent on the next slide. So a little more depth on the coordination number. How many donor atoms are coordinated? We normally see 4 or 6, and we explore it more in 23.4. If I have a 4 coordinate, it's a tetrahedral, or it could be a square planar. You'll see that on the next slide. If I have a 6 coordinate, it'll be an octahedral. Think back to VSEPR. We talked about these things back in 1210. Now, the coordination number is influenced by size. If I have a bigger ligand, Cl minus is greater than F minus, I can't put as many atoms or ligands around that central metal ion. And if the ligand has a charge, notice when the ligand has 0 charge, there are 6. When the ligand has a -1 charge, there are only 4. Charged ligands have fewer ligands will surround the metal. These are just factoids. I can't say they're anything else but that. To wrap up this section, I want you to focus in on what does this look like in 3 dimensions. We'll need this when we talk about isomers. Here are the geometries. Both of these are octahedral. Remember, we would have something in the center, and we would have 6 atoms radiating out. Now it turns out the center is the Lewis acid, and radiating it out are the Lewis bases, all of which are called ligands that share a pair of electrons. We could also have something as a tetrahedral, and here we have zinc. It makes a complex which has 4 ammonias rearranged as a tetrahedral. Here we have a different metal, platinum, and it has the ligands, and they are arranged as a square planar. Where does this come from? Well, remember back in chapter 12, we talked about crystal structures. Someone would make a crystal, and then they would study their crystal structure and figure out what the actual geometry was. And that's the end of this section.